So today we are going to be talking about the y-intercepts, the x-intercepts. Oh my gosh, look at that. I have a typo in my paper. There is. I just noticed that. Vertex and symmetry. No, I have algebra all day. So I got 5 of them in a row. Do it? Kind of like it. I do. Okay, so x-intercepts are where the function crosses the x-axis which you probably already knew prior to coming to this class. But it's where it's going to cross the x-axis, and another really important piece of information is that it's also when y equals 0. Which makes sense, right? Because if we are looking at the x-intercepts here and here, the y value is 0. Right?
My lines look like that. The lines of the graph.
Okay, so we're going to look at the x-intercepts. We're going to solve them numerically, graphically, and algebraically. There are 3 different methods to finding the x-intercepts. Numerically means you're going to be looking at tables, numbers in a table. First of all, I don't like this example, so you can go ahead and cross it out. Okay, when we're looking at a table and we're looking for the x-intercepts, remember we're looking for when y is 0. So looking at this first table, I see that y is 0 right here. And 23. We don't have 23. Isabella, where is the other x-intercept in this table?
This one, x-intercept?
Uh-huh.
Oh, the 0, 0.
Yes, very good. 0, 0 is the other one. And you're right, -4, 0 is the second one. They're both x-intercepts. So -4, 0 and 0, 0 are both x-intercepts. Now, you can have unlimited amount of x-intercepts. Right. The function can cross the x-axis as many times as it wants to. So when you're given a table, you're only given a piece of information. So it might be a good idea to just sketch the graph of it as a whole, just to make sure you're not missing anything. Because like I said, a table only gives you like a little bit of information as opposed to the whole thing. So I always recommend, if you're given a table, just to plot out the points just real quick. It doesn't have to be super accurate. -6 2's over here. -4 0's right here. -2, -2's right here. 0, 0, and 2, 2. So then you can see that, yes, I have an absolute value function, and it is going to cross it twice and only twice. Right? So it's always just a good check, just to make sure they're not trying to trick you or anything by not giving you all the information on the table. All right, next table for Brianna. So Brianna, does the y value, or do the y values, do they ever equal 0? When? No, the second table. Second table.
No.
No, they don't. Not in the second table. Yeah, we're done with the first table. In the second table, they don't. So, like I said, plot your points just to make sure you're not missing anything. -2, -6, -1, -3, 0, -1, 1, -3, and 2, 6. All right, so after I plot my points, I do see, do I have any x-intercepts? No, right? Because it's never going to come back up here and cross this axis right here. Because your function is going down forever. So your answer would be none. But it's always a good idea to check. You don't have any y's in the table, or y equals 0s in the table, so you're thinking none. Graph it just to be sure. Okay. If you're looking at the graph, it's a little bit easier. All you gotta do is look at the picture. So let's see, 15. That is quaternion. What is the x-intercept if there is any? Do what? Very good, there isn't one. So you would put none. Okay, 24, Jasmine. How many x-intercepts do I have in this graph? Very good, 2. Tell me one of them. Sorry, my graphs are so small. You got it backwards. Flip it around. 2, 0. Yes. 2, 0. 2, 0, and then 16. Kiadra? Tell me the other one. Very good. -3, 0. Okay. 5. Gipram. Tell me the x-intercept for this one. 3, 0, very good. And 8. We don't have an 8, so Josh. Oh, wait, you're an 8?
Yeah.
Oh, I'm sorry, just kidding, we have an 8. What's the x-intercept for this one? Careful, that's the y-intercept.
No, that's what I was doing.
So is it ever going to go down and cross the x? No, so none. It's got that asymptote as a boundary, so it's never going to go cross the boundary and go down, so none. Okay, next, algebraically. Yes, you could plug this into the calculator and probably get the x-intercept that way by looking at the graph, but that would be, once again, doing it graphically. So I want to show you the algebra method to finding x-intercepts. Remember this piece of information that we know. We know that y equals 0. Okay? So what number am I going to plug in to y to find the x-intercepts?
0.
0. Very good. All right? And so then if I solve for x, that will give me the x-intercept. So 18. Do we have an 18? Okay, now Josh, tell me, what is the first step to solve for x? Yes, you do. Remember reverse PEMDAS. Are you adding or subtracting anything? Well, yeah, what are we going to subtract? The 7. Very good. So we're going to subtract the 7 to both sides. 2. Leslie. What's next?
You divide by 2.
Very good. Divide by 2. And so then x equals -7/2. And that is my x-intercept. Fractions are a good thing. Leave stuff in fractions. If it's a decimal, it's okay. But normally you'll see stuff in fractions. Alright, so then that's how you solve it algebraically. So, the second one, what am I going to plug in for y? 0. Let's just do this one a little bit faster. What's the first step? Yeah, subtract 8. Okay, what about next? Very good, divide by 2. Okay, divide by 2. Alright, now I have the square here. Alright, the square. Does anybody know how to get rid of that? Very good. Square root. Someone said it over there. Square root. So we're going to square root one side. We're going to square root the other. Okay, so I'm not going to have you do this by hand yet. Eventually we will, but for right now you would always be able to plug that in your calculator to see what it is. You actually cannot take a square root of a negative number. So if you plugged it in your calculator, it would give you error. Right? So it would give you an error. So what do you think that tells you about the x-intercepts?
None.
Very good. None. All right. Questions, comments, concerns about x-intercepts
Wait, so you can never get the square root.
of a negative?
Okay.
Yep. All right, let's go to y-intercepts. It's pretty similar. Y-intercepts are where the function crosses the y-axis and also when x is 0. Alright, so it's where the function crosses the y-axis, and it's also when x is 0. Alright, for the y-axis, you will only have either no y-intercepts or 2 y-intercepts. Or I'm sorry, scratch that. No y-intercepts or 1 y-intercept.
Not two.
Not 2. Not ever 2 or more. Just 0 or 1. The reason being is because if you had, you're not ever, but if you did have 2 y-intercepts, your graph would have to cross through both of those, right? And now, is it a function?
No.
No, because it doesn't pass the what? Right, the straight line test, pencil test, vertical line test. Right, you remember hearing that? Mm-hmm. So that's why you'll never have 2 y-intercepts. It'll always be either none or just one of them. So none or just one. Messed up what I said. All right. So either none or 1. Those are your only options, none or 1. Okay, so on this first table here, look at the table and look to see when x is 0 and let's see, number 9. Who's 9? Angie, what's my y-intercept on that first table? Very good, -1. So here's my y-intercept, 0, -1. All right, 17, Briseda, right? Does x ever equal 0 on this other table? No, it doesn't. But like I said, make sure you're graphing just to be sure. Just to be sure. So -6, 2, -4, 0, -2, 2, and 2, 2. Take a second, plot those points. So if you were to connect the dots of these points, is it crossing the y-axis? Yes, it is. So that's what I'm saying. Sometimes they might leave out a piece of information on that table, and so just be really careful. What would the y-intercept be?
0.
Yeah, I'm going through the origin. 0, 0. All right, any questions about that? Good? All right, when you're looking at the graph, Kind of similar. Remember, everything has an arrow. Everything has an arrow. Well, not everything, but if it has an arrow, it's extending forever and ever. So even if your function stops, you have to pretend like it goes on forever. So on this one right here, it's actually crossing the y-axis at what point?
2.5.
Yeah, close enough. I'm just going to say 2 to keep it even. I just didn't do a very good job drawing. All right, so let's pull some sticks. 19. Caitlin, what about this one? Where is it crossing the y?
0.5.
Very good. 0, 5. 14. Faith, where's it crossing this one?
Can you pick my stick up? Is that good? Okay. Where's the 1?
Negative 1. Good. 0, negative 1. And 3. Oh no. Wait, I know it. Paloma? No. And A. Ariana. Ariana, where is it crossing the y-axis here? 0, 4. Very good. Okay. Algebraically, I know most of you probably know that the second number was going to be your y-intercept, but I'm just going to show you kind of the algebra way why that happens. Am I going to be plugging in 0 into the y or into the x? Into the x, because x equals 0. So when you plug in 0 here, what's 2 times 0?
0.
What's 0 plus 7?
7.
7. So y equals 7. Same thing on the second example. We're going to plug 0 in. Remember order of operations, we have to square first. So 0 squared is 0. 0 times 2 is
0.
plus 8. 8. Did you have a question, Isabella?
No.
Okay. All right. So we did x-intercepts, we did y-intercepts. Any questions on the front of the notes? All right, good news is that was like 80% of the notes. The back's going to go by much faster. Okay, vertex. You probably have heard the vertex term before, right? The vertex is going to be where your function changes direction. All right, it's where your function changes direction. All right, so go ahead, draw in the absolute value function. And it's changing directions right here at this corner point. So that would be where your vertex is. And remember, your function, it can be shifted all around, so your vertex can move, but it will be this corner point right here. Okay?
Can you say that again? I didn't register.
Yeah. The vertex, it can be shifted, the function can be shifted all around, which means your vertex is going to be shifted all around. So it's always going to be this corner point, but depending on where your v goes, will depend on where your vertex is. Same thing for quadratics. Your parent function, your vertex is right here. But depending on, once again, how your function, if it gets moved, your vertex will also be moved, so it won't always be right here at the origin, but on the parent it is. Okay, and then the even radical We're going to call this point where it stops. It's not really changing directions, but it is going to stop right here. We're going to call that a vertex as well. All right, so those are the three functions that are going to have vertexes out of all the ones that we've talked about. So the absolute value's got one, the quadratic's got one, and then the even radical will have a vertex because it will stop at that point. Any questions about vertex? All right. Point of inflection. That's probably a new term, right? We haven't heard of the term point of inflection, right? Good. A point of inflection means that it's changing something called concavity, which I think is also a new term, right? All right. We're almost done. I'm sorry notes are so long today. Changes concavity. Changes concavity. When I mean changes concavity, I mean that your function is going from either a happy face to a sad face. Oops, hold on, let me draw a sad face. Sad face. Or vice versa. Sad face. So you're either going to go from happy to sad or sad to happy. That's what I mean when I'm saying it changes concavity. So let me draw my picture and it'll make a ton of sense. Draw a cubic. Draw an odd radical. If you look at your function right here, you put 2 dots. Do you see how it's a sad face? It's a sad face all the way up to this point. Because then if you put 2 dots, it's now a happy face. Right, so see, you got 2 eyeballs here. You see how it's sad? Up until this point where it becomes happy. That's the point of concavity. Or I'm sorry, point of inflection. You're not the first person that said that today. All right, so it's where your function goes from sad to happy. It's called a point of inflection. So then same thing over here. You go from happy face to sad face. So this point right here is your point of inflection. Fine. All right, so going from sad to happy or happy to sad, that's when you're going to get the point of inflection. Any questions on that? I know it's a new term. You'll see that word a lot in pre-cal calculus when you take that.
It's kind of like inflection. Reflection, sorry. Wait, what's after algebra 2?
You can either choose to do pre-cal or college algebra. I'll talk more about it after notes.
Will you get AP?
All right, let's do symmetry. And I would explain it, but I don't want to use up my recording time explaining it, so I'll do it after I do notes. Okay. Symmetry. We have rotational symmetry and reflectional symmetry. Before I get into symmetry, I want to talk about the linear function real fast. All right. Before I even get into it, I want to talk about the linear function. Oh, where'd my linear patty paper go? Oh, there it is. Okay. The linear function is kind of special when it comes to symmetry. Because you can, well, okay, first of all, for a reflectional, you can fold the linear graph on any line and it's going to reflect, right? So there is an infinite number of lines of reflection for a linear graph. There are also infinite number of points of rotation, because no matter what point we rotate this on, you're going to get the same linear function. So linear is kind of special because there's so many different types of symmetry for this. So if I asked you anything on the homework, it might accidentally ask you for symmetry on a linear graph, just put both. All right, so for linear only, linear is kind of special. To describe the symmetry, just put both, just because there's so many different types. All right, so you can't get specific with the type of symmetry it has. It has rotational, it has reflectional. We're just not going to get specific with it. Just put it has both types of symmetry and leave it at that. All right. Some of these other functions, though, we can get more specific with the types of symmetry. Let's do reflectional first. I'm looking for two functions that can be reflected from around the room. Quadratic, right? If you fold the quadratic in half.
Yeah.
Very good. Quadratic and absolute value. All right, the way that you would describe the symmetry, let's draw just the regular absolute value function first. The way that you would describe the symmetry, and you can abbreviate if you want, you're going to say this. This has reflectional symmetry. All right, so you can abbreviate reflectional and symmetry, because I know those are both long words. It has reflectional symmetry across, oh, I spelled across wrong. Sorry, I spelled across wrong. Across. It has a reflectional symmetry across, and then you have to put the line that you're folding it on. What line are you folding it in half on? You can put the y-axis. You could also put the line x equals 0. Either one. So, on that one, we're folding it on the y-axis, and then that is the line of symmetry. That's the only line you can fold it on for it to have reflectional symmetry. So that's how you're going to describe reflectional symmetry. Reflectional symmetry across, put the line. So let's say that we moved our quadratic function over 4. All right, so 1, 2, 3. So this is at 4, just because I know your graphs are kind of tiny. Bless you. All right, so what line? I would say that this has reflectional symmetry across. What line am I folding it on? Very good. X equals 4. I know some people get confused about whether this is going to be x equals or y equals. The way you remember that, your line is going through the x at 4. So it's x equals 4. Because you're going through the x. Does that make sense? All right, so wherever you can fold it in half and it matches up, that's your reflectional symmetry. Let's talk about rotational symmetry now. Let's talk about rotational. Just an extra, but in case you didn't get it, but I think you got it. You got it right? We're good? Okay. All right, rotational symmetry. I got 3 functions that have rotational symmetry. Cubic, very good. Cubic. What's another one? Odd radical, good. And one more? No.
Rational.
Yes, rational. Cubic, odd radical, and rational. So let me show you. I'll put this back up right now. Cubic function. T's at the top, right? If you were to rotate it about this middle point, oh geez, hold on, sorry. If you were to rotate it about this middle point right here, is that not the same function? Right? And you rotate it 180 degrees. So we flip it upside down, and it's still the same function. Okay? For the rational, you put it right here where your asymptotes cross. Right? At that middle point where the asymptotes cross, is it not the same? I rotated it right. Right? So it's the same. And then the last one, radical, the odd radical. And if we were to rotate it 180, if I got my finger out of the way, it would be the same. Make sense? So, how I want you to describe it, how I want you to describe the rotational symmetry. It's similar. You're going to say it has rotational symmetry. You're going to say about the point it rotates. So in this example, you can say 0, 0, or you can say the origin. So there's a point, there's like that middle point that you have to rotate it about for it to be the same function. Otherwise, you're going to be switching quadrants, which won't be good. So you have to say rotational symmetry about, and then that middle point, the point of inflection on these guys, that point right there is where you're rotating. All right, so then if we had a cubic that looked like that, and just so you know where this point is, over 3, up 3. So this point right here went over 3, up 3. I can't zoom in when I'm recording. That kind of sucks. If I moved it, I would describe the symmetry as rotational symmetry about 3, 3.